Welcome to Lecture Online, and here's the second item that we really have to understand before we could figure out the distance to stars farther away than those we can measure with the parallax angle. In the previous video, we're looking at Wien's law. Here we're going to look at what we call the Stefan-Boltzmann's law. And the Stefan-Boltzmann's law is a law that was developed in an understanding that the amount of light or the amount of energy being emanated from a star depends not only on the temperature but also on the size of the star, because obviously if a star is bigger than another star, there's more surface area, and if the amount of radiation per unit area is the same for both stars, and of course the bigger star will emanate more energy than the smaller star. And so they came up with an equation where the amount of radiation per unit time, which is dq dt, another way of looking at dq dt is simply saying it's the luminosity of the star, the amount of energy being radiated by the star, is proportional to the surface area of the star times the temperature to the fourth power. And that was a powerful equation. Now actually this is the proportionality. The actual equation, if you're interested, the equation dq dt, or we can just say the luminosity of the star, is equal to the emissivity of the star, and that's a property that depends upon what the material is made of and so forth. For stars, E is typically about 1, some constant sigma times the area times the temperature to the fourth power. But we're only concerned about those two variables of the equation. So it really is proportional to that, and that's all we really need to know at this point. So it turns out we want to know what the surface area is, and we want to know what the temperature of the star is. But at this point, we just want to do the comparative kind of analysis. So let's say we have two stars. They're the same kind of stars, same blue stars or white stars or orange stars, doesn't matter. And one star, star 1, has a radius of r and therefore an area of a. Here we have another star where now the radius is 2r, and because the radius is double, the area will be 4 times as much. And the reason for that is because the area of a star is proportional to the radius squared. So if you double the radius, you'll have 4 times the area. The equation, of course, for the surface area of a sphere is 4 pi r squared. And so therefore, a star that is twice as big in diameter or twice as big in radius will be 4 times as big in area. And if it's 4 times as big in area, it will then, of course, radiate out 4 times as much energy. On the other hand, let's say we have two stars that are the same in size, but they're different in color. Now we will learn soon enough that that's not possible, but just for the sake of argument, let's assume that is the case. We have two stars that are the same size, same surface area, but this is an orange star where the surface temperature is 5,000 Kelvin, and here's a white star where the surface temperature is 10,000 Kelvin. So this star is twice as hot as this one. Well, notice here that the equation or the proportionality says that the amount of heat generated or the amount of luminosity of the star is proportional to the area and the temperature to the fourth power. Wow, what does that mean? Well, let's find the ratio of those two stars, the ratio of the temperature. So if we divide the 10,000 Kelvin divided by 5,000 Kelvin, it shows us that this star is twice as hot as this star. Well, that's straightforward enough. And so if we then take this ratio and raise it to the fourth power, this tells us that this star will put out 16 times as much light as this one. In other words, two stars, same size, this one is 10,000 degrees, this one is 5,000 degrees at the surface. This star will emanate 16 times as much light. This star will be 16 times brighter than this one. Size-wise, this star will be 4 times brighter than this one. All right, now let's put it together. Typically, white stars are bigger than orange stars, and we'll learn later how much bigger. So let's imagine for a moment that this here is the white star. So I'll simulate white star by doing this little dashed line. So this indicates now that this becomes a white star. And let's say that this here is an orange star. So we'll turn this into an orange star. And so therefore the temperature of this one would be 5,000 Kelvin, and the temperature of this one would be 10,000 Kelvin. Okay, so not only is this star bigger, it's also hotter. Now, with the two combined, based upon this analogy right here, how much more light does the bigger white star put out compared to the smaller orange star? And so we can then say that the luminosity of the white star is equal to, now we have to take care of those two proportionalities. For the temperature, it's a ratio of 16 to 1. So it's going to be 16 to 1 times more bright, 16 to 1 more luminous. So the white star is going to be 16 times brighter or more luminous than the orange star simply because of the temperature. But not only that, because of the size, it also has 4 times the area, so it's going to be 4 times as luminous simply because it is bigger. So we multiply that times 4 to 1, and it turns out that this white star, being twice as big in diameter, therefore 4 times as big in area, and twice as high in temperature, twice as hot, that the luminosity will be 64 times the luminosity of the orange star. Wow, now we have a great tool in our toolbox. Not only do we figure out what the temperature stars were because of Wien's law, because of Stefan Boltzmann's law, we can use that to our advantage to say, wow, if we know the temperature comparison from one star to the other, we know there's luminosity difference. We know that one is brighter than the other and by how much. And if we can find out how big stars are, then we can also find their luminosity difference because of their size, and we can put them together. So if we know the relative size of the stars and we know the relative temperature of the stars, then we know their relative luminosity. We know how much brighter the one is compared to the other. One way to look at this difference, let's say you had one white star. How many of these orange stars that are half the diameter and half the temperature, how many of these orange stars would you need together to put out as much light as one of these? And the answer would be you need 64 of these stars to put out as much light as one of these. So that was a tremendous powerful tool in our toolbox when we understood Stefan Boltzmann's law. So with Wien's law and Stefan Boltzmann's law together, we now had a pretty good understanding about the luminosity of stars based upon their temperature and the luminosity of stars because of their size. Now, who was smart enough to take that information together and utilize it to understand the distance of stars? If you want to know that, stick around for the next videos and you'll see how. Welcome to iLectureOnline, and now we're going to take a closer look at the Stefan Boltzmann's law and that concept where the amount of radiation per unit time or the luminosity of a star, the QDT, is proportional to the surface area of the star and temperature to the 4th power. What does that tell us? What kind of information can it give us? And it turns out it will enable us to figure out how big stars are. Let me show you why. Let's say we have 2 stars. They're both the same size, but they're at different temperature. Now we know in real life that's not going to be the case, but let's say for the sake of argument it was. So we have a red star at 3000 Kelvin on the surface temperature and a yellow star that has a surface temperature of 6000 degrees. And I don't have a yellow pen, so this represents a yellow star. If they're the same size, you can then say that the luminosity of the hotter star will be, since the hotter star is twice as hot as the colder or the cooler star, I shouldn't say cold star because 3000 degrees is still very hot. But if the ratio of the temperature is 2, I take 2 to the 4th power because that's what it says right here. The proportionality is temperature to the 4th power. So if it's twice as hot, I take 2 to the 4th power. That means I would expect the yellow star, the hotter star, to put out 16 times as much radiation or 16 times the luminosity of the red star. But what if we understand that the yellow star will be bigger and we want to know how much bigger? Well, let's say that in our example, the yellow star actually is 48 times as bright as the red star. So only 16 times as bright can be accounted for the extra temperature. That means if it's even brighter than that, it must also be bigger. And the question is, how much bigger? Well, we can see then that the increase in luminosity due to the increase in size would be 3 times, right? So if we then take 48 and divide it by 16, that is 3 times as bright due to the size of the star. So now we can say that because of that, the area of the yellow star is equal to 3 times the area or the surface area of the red star. Since it's 3 times as bright than I would expect it to be if they were the same size, right? So now since we know that the area is 3 times the size, the surface area, then the red star, we can then say, well, since the area is 4 pi r squared, and so we can then say that 4 pi r squared of the yellow star is equal to 3 times 4 pi r squared of the red star, right? So simply replacing the area by what the surface area of a sphere is equal to. Then cancel out the 4 pi on both sides, and then if I want to find the radius of the yellow star, I can then say that the radius of the yellow star is therefore equal to the square root of 3 times the radius of the red star. I that because I took the square root of both sides. That means that the squares disappear, and I get the square root of 3. And of course, the square root of 3 is about 1.72. So that means that's equal to 1.72 times the radius of the red star. Now, this may not be the actual proportionality, but at least it shows you what methodology they use. So now they realize that if they knew the temperature of the stars, they can then measure the luminosity of the 2 stars. And then if the 2 stars were different in luminosity other than would be explained by the difference in temperature, which is simply a T to the 4th ratio, then they knew that the remaining increase was due to the area, the size of the star. And so then if they said, well, the increase of the area must be that many times, or I should say the area must be that many times bigger than the area of the other star, because all we do is take the actual luminosity difference divided by the luminosity difference accounted for by the temperature, and we get the luminosity difference due to the area. We take the square root of both sides, and now we know how much bigger the yellow star is compared to the red star. Great stuff. One big problem. How do we know the actual luminosity of the stars? If we don't know how far the stars are. Because we look at 2 stars, we don't know how far they are. One appears a lot brighter than the other, but it could be because it's a lot closer. Not because it's bigger. So the problem still came in. Even though they understood Wien's law, they now understood Boltzmann's law. They saw how the Boltzmann's law can theoretically give them the size of the star. They still couldn't apply this equation if they didn't know how far it was to the stars. But some very intelligent, very smart astronomers came along and go, I think we can figure out how to do that if we could just know how far the stars were. Maybe you already know where I'm going with this, but if you're interested, stay tuned. It's coming up in several more videos. Welcome to Lecture Online, and here our 3rd video on the Stefan Boltzmann's law will enable us to fully understand the complexity in trying to figure out the distance to the stars beyond what we can measure with the angle of parallax. We already discovered that with Wien's law we can figure out the temperature of a star simply by looking at its color and the predominant wavelength we get from the star. With the Stefan Boltzmann's law, we also realized then that the amount of radiation, or the luminosity of a star, is proportional to the size of the star and the temperature to the 4th power. And in the last video we saw how we can then make out, if we know the temperature difference by looking at the color, we will know the size relationship between 2 stars. We can do that by measuring their luminosities, by how bright they appear. But there's one more problem, because we also realize that the luminosity is proportional to 1 over the distance squared. Now, in this case, the R stands for distance away. So we like to use the radius, R for radius, but R also stands for distance, how far away something is. So maybe, so that we don't confuse one another, let's turn this into a D. That may make it a lot simpler for people to look at, so we don't confuse the distance to the star with the radius of the star. All right, so now let's imagine for a moment that we're looking at 3 identical stars. Identical in terms of temperature and size. Let's say 3 white stars, they're all 3 at 10,000 degrees Kelvin, and we measured the luminosity. In one star we measured the luminosity to be 4 times as much as the 2nd star, and the 3rd star only 1/4 the luminosity of the 2nd star. Now, you realize that they're all the same temperature, and let's assume that they're all the same size. Why would one star appear brighter than the other? Well, the answer is simple, because it's closer. So there's this relationship between the brightness, how bright a star appears to us, and how far the star is away from us. So by knowing that, can we know how far one star is relative to the other? Well, let's figure that out. So here, if that is true, we can then say that the distance is proportional to 1 over the luminosity, and then we take the square root of that, so it would have to be the square root of that. So if we rearrange that proportionality equation, and we put distance up there and luminosity down there, we take the square root, we can then say that the distance is proportional to 1 over the luminosity, 1 over the square root of the luminosity. So let's figure out where this star is relative to this star. Well, let's see here. So how do we work that out? Let's say, since this star is brighter, it will be closer. The question is, how much closer? Well, it depends on the relative luminosity. So what we're going to do here is that the distance here is proportional to 1 over the difference in the square root of the difference in the luminosity, which means that the distance therefore is proportional to 1 over 2. All right, so that means if the difference in luminosity is 4 times, that means the difference in distance is twice. That means this will be half the distance of this star, or this star will be twice as far away than this star. And in the same token, if this is 1/4 the luminosity, that means that this star must be twice as far as this star, and that star must be 4 times as far as this star. So that's by knowing the relationship between the luminosity or intensity or brightness of an object and the distance, we could then say if they are all the same size and they're all the same temperature and the luminosity is different, from this proportionality we should be able to figure out how far they are relative to one another. The problem is we still don't know how far they actually are. So here we have 3 things. We have the temperature of a star, which is easily identified by using Wien's law, not a problem. The size of the star is a little bit more difficult. We can find their relative size but not their actual size because we don't know the distance to the stars. And we can find their relative distance but not their actual distance because we don't know their actual size. So here we are, 3 things. Temperature, because of their color, the distance to the stars, and the size of the stars. And 2 of those 3 things, we can find the relative size and the relative distance, but not their actual size and their actual distance. To find their actual distance and their actual size, we need to find the true measure of one of those 2 quantities. If we find the actual distance to the stars, we can find their actual size. If we can find their actual size, we can find their actual distance. But we have to have one of those 2 unknown quantities. And as long as we don't have one of those 2 unknown quantities, we can't really find the true distance to the stars. And that was the big challenge at the time. When we go back about 130, 140 years, people were really scratching their heads saying, how do we figure that out? And in the next video, I'll show you the key. There were 2 very smart astronomers. One of them, his name was Hertzsprung, and the other, his name was Russell. And independently, they thought of the solution to this big problem right here. So if you're interested, come to the next video and take a look how they did it. Welcome to Electron Line, and continuing in our quest to determine how they figured out the distance to the stars, the distance to the galaxies, this is everything in our universe. We get to the next stage here, and remember what we talked about earlier in a previous video, that they had already figured out how to find the distance to the 100 nearest stars using the angle of parallax. When they observe stars from a position of the Earth over here with respect to the Sun, and then 3 months later, when the Earth is over here, now a distance of 1 astronomical unit away from the Sun in the other direction, they take a look at the same star, they can measure the angle between those 2 points of observation, and that's called the angle of parallax. And the distance to that star then in parsecs is determined to be 1 over the angle as measured in arc seconds. And typically the angle is somewhere around the fraction of an arc second. For example, if let's say theta was equal to 1/3 of an arc second, so the arc second symbol is like a double line like that, and therefore the distance would be equal to 1 over 1/3, which is equal to 3, and of course the units would be parsec, where a parsec is 3.26 light years, so it would be about 10 light years. So they were actually able to figure out the distance to the nearest 100 stars. Now once you know the distance to the star, and you know the apparent magnitude or the apparent brightness of the star, you measure how bright the star is, you can actually figure out how bright the star really is, not the way it appears to us, but the way it really is. You can actually figure out the luminosity of the star. Well, they did that. Well, who did that? Well, it turns out there are 2 individuals, Hertzsprung and Russell. Hertzsprung was a Danish astronomer, Russell was an American astronomer, and independently, they probably didn't know from one another that they were doing this, they began to come up with this idea to try and plot the actual luminosity, the actual brightness of stars with respect to their color. And also, they were able to figure out the actual brightness of the stars by measuring the distance using the angle of parallax. So they did that and began to plot the results on a chart where on the vertical axis it indicates the luminosity of the star, the actual luminosity, not the way it appeared to us, but the way it actually was, knowing how far the stars was. They could figure that out. And also versus the color of the star. And of course, we have already learned that with Wien's law, the color of the star is associated with the temperature of the star, which is associated with the wavelengths of the radiation that's being emitted from those stars, anywhere from 400 to 700 nanometers, depending upon if it's a blue star or a red star. Now, when they began to plot those dots on the chart, each dot representing a star, and so they came up with about 100 dots, they saw something extremely interesting. So they started putting the dots down, and to their surprise, as they were developing this, the dots all appeared to be in a line. And so imagine they ended up with 100 dots. Vast majority of them were like this, and some of them were over there. And that's the result they ended up with. Something extremely interesting. But first of all, they didn't know what this was, why there were some stars there. Now obviously, remember, if you understand the chart here, the higher you are on the chart, the brighter the star is. The lower you are on the chart, the dimmer the star is. And here I had a bunch of stars that were very hot on the surface, whitish in color, but very, very dim. Much less dim much less bright than the sun, because this represents the brightness of our sun. So if this is equal to 1, that means it's a star just like our sun with the same brightness as our sun. As it turned out, if you draw a line over here and then draw the line down here, notice that a sun, our sun, would appear about there on that chart. That's kind of interesting. So that shows that of the 100 nearest stars, the sun was one of the brightest of those 100. There were only about 5 or 6 stars that were brighter than the sun, and all the other stars were less bright than the sun. The vast majority of the stars were either of the orange or red type, and very few were yellow, and there was only about 1 or 2 or so that were actually white stars, except for the ones that were down here. They were whitish in color, but they were very, very dim. But this was a very interesting result, because what they're seeing here is that there's a general, and let me use a different color here so we can see this. There's a general relationship between the color of the star, the temperature of the star, and the brightness of the star. Now, when they started looking at this, we already knew that the amount of luminosity of a star depends on 2 things. It depends on the size of the star, and it depends on the temperature of the star. But this increase from red to orange to yellow, notice that it goes from 3,000 to 4,000 to 6,000 degrees Kelvin on the surface of the star. Notice that that alone would not account for the large amount of increase in the luminosity. Remember that if you go from a red star to a yellow star, and if the size of the star stays the same, this star should only be 16 times as bright as this one, because according to the Stefan Boltzmann's law, it's proportional, right? The luminosity is going to be proportional to the temperature to the 4th power. So if you double the temperature from 3,000 to 6,000, if you take 2 to the 4th power, that's only 16. So the curve should have looked like this rather than like this, if the only result was that the star was getting hotter, not larger. So then the result also indicated that not only was the star getting hotter as you go to the left on that diagram, they're also getting larger. So the stars are becoming larger and larger and larger as they went from red stars to orange stars to yellow stars to white stars. So we can graphically indicate that. So what Hertzsprung and Russell began to realize is that these were probably pretty small stars, and then as you go further and further and further up this chart here, the stars got to be bigger and bigger and bigger. So that was a tremendous discovery. Here they could see that there was a relationship that was able to be determined between the color and the size of the star, and therefore also the luminosity of the star. That was a huge discovery. Now back to these stars. What were these stars? Well, they were white, but since they were not very luminous, they had to be very, very small. So these were termed to be very tiny little stars, and so they named these little stars the white dwarf stars. In a later video, we'll learn what these white dwarf stars. Or simply white dwarfs, they're called white dwarfs. We'll learn later what those are, but at least this was the important part of the diagram. So what did that imply? This had a tremendous impact in our ability to determine the distance to stars. And why is that? Because let's say we're now looking at a star that is much further away than the hundreds near stars. Remember, this technique was only good out to about 15 or 16 light years. So let's say there's a star that's 50 or 100 light years away, and we're measuring the brightness of the star. And then we're wondering, well, how far is that star? Well, unless we know the real brightness, the real luminosity of the star, we couldn't figure out that distance. However, if we say, well, wait a minute, if we can take a look at that star and we can measure the color of that star, we can then place it somewhere on this diagram. And so let's say that we ended up with indicating that it was somewhere between the orange and the yellow star, and say, okay, it must be right there. All right, then we would be able to tell that by the wavelength of the light coming towards us. And then we'd go ahead and move this over here, and we would be able to determine the luminosity of the star, not just the way it appears to us, but the way it actually is, the real luminosity of the star. So now we would have the real luminosity of the star, we would have the apparent luminosity, and with those two indicators, with those two results, we could actually find the distance of the star. Remember, there's three things you need to know. You need to know the distance of the star, you need to know the actual luminosity, I'll just go ahead and put it like that, and the apparent luminosity, how bright it actually or how bright it appears to us. If you know the apparent luminosity, you know the actual luminosity, you can calculate the distance to the star. Or if you know the apparent luminosity, you know the distance, you can figure out the actual luminosity and so forth. As long as you know two items, you can always calculate the third. But the key here is that we're now able to calculate the distance of stars knowing this relationship from this diagram. This diagram forevermore has now been called the HR diagram. So that's the name. And notice that H and R are the first letters of Hertzsprung and Russell, the two that invented this diagram. Of course, since then we've vastly expanded on this diagram with gaining more and more knowledge, and you'll see in the next video how we've been able to use that in various ways. But the HR diagram was now actually able to give us the tools necessary to figure out the distance of stars well beyond 15, 16 light years to thousands of light years, and it opened up a whole new concept, a whole new understanding to the universe, and many more discoveries were made based upon our understanding of stars. So let me show you in the next videos why that was so important. With the groundbreaking work that Hertzsprung and Russell did, inventing this HR diagram, over the years we of course expanded upon it a lot with their help. And this is what typically a modern day HR diagram looks like. So notice there's many more stars because we've been looking at thousands and thousands of stars. Place those stars on the HR diagram, get a much better picture of what the HR diagram looks like. And notice that the vast majority of the stars are lying along this line here. Now notice it's no longer a straight line, has a little bit of an S curve to it. And they now call that region here on the diagram. Now remember, this is just a diagram region. It's not a physical region out in space. It just represents something about stars. It just represents that these are the stars that are in their main cycle of life, their main sequence of life as they call it. So therefore we call this the main sequence. Let's write that down, the main sequence. And so what we have discovered since, that this is the stage of the cycle of the life cycle of stars where they're simply converting hydrogen to helium in their cores. So this is the stage what most stars that you see out in the universe are in at this moment. Our sun is in that stage, is peacefully converting hydrogen to helium. And there's also the stage of the star's life that takes the most or the longest time to go through. Then we've discovered that these stars then at some point begin to change. Now notice these dots over here. What do they represent up here? Well, notice they tend to be orange or red in color, and they're extremely luminous. That means they're cool on the surface, yet way, way brighter than the stars in this region right here, which have a much hotter surface. Well, cooler surface should normally mean much less luminous, but if they're that much more luminous than the stars over here, they must be much, much larger, and that's indeed the case. These are called red giant stars, and the ones that are way up here are actually called red supergiants. So these stars have grown to enormous size, and that's because now at the core of those stars, a different kind of nuclear fusion process takes place. In those stars, instead of converting hydrogen to helium, they tend to convert helium to carbon, which is a much more ferocious nuclear process, generating a lot more heat, expanding the stars to enormous sizes. So those are what we call the red giants. And you can go out at night in the sky and look around and see those red giants out there. And you can see red giants to very large distances because they are so large and they are so luminous. Now here, notice here the little white dwarfs, and it turns out that the white dwarfs are typically the end stage of a star's life. So what typically happens is a star becomes a main sequence star, then eventually becomes a red giant, and then eventually becomes a white dwarf. And as a white dwarf exists in the universe for billions and billions of years, it slowly begins to cool down, and as the white dwarf stars cool down, from white stars they become yellow stars, they become orange stars, and red stars, and eventually brown stars, black stars, and kind of disappear out of sight. But that's generally the end stage of a star right there, where just the core of the star survives. It shrinks down to fairly small size, that's why they're so dim, and then they slowly cool down over the billions and billions of years. So we've been able to figure out the life cycle of stars by this HR diagram as well. And in some later videos, I will go through the details of how we actually discovered that and how we can then piece all that information together to really understand what's going on in stars. But what we're interested in here is ultimately how to find the distances to stars. So remember, before the HR diagram, we could only find the distance to maybe the 100 nearest stars, but now we can find the distance to thousands upon thousands, millions of stars really. All we have to do is take a look at a star with a powerful microscope, measure its apparent brightness, how bright it appears to be, then by the color of the star, determine where on the HR diagram it would end up. And remember that these are the very small stars. Sometimes they're called the red dwarf stars. And so these are bigger stars and bigger stars and bigger stars. These are stars the size of the sun. These are bigger stars again. And you can see that these stars up here must absolutely be enormous, because this is not a linear scale here. This is a logarithmic scale. And yes, indeed, there are stars that are as much as 1 billion times as bright as the sun. So one of those stars gives off as much light as 1 billion suns. So those are enormously large stars with very hot surface temperatures. Notice the letters down here. Those are called the spectral types of stars. So we classify them as O, B, F, G, K, and M stars. Our sun being a G class star. So that's a spectral class G. Now, notice that once we have this association between the color and the actual luminosity. So from this chart, anytime we find a chart and we find its color, we can find its luminosity. And from its luminosity, we can then go measure its apparent luminosity, and from that we can measure its distance. So that's now how we know how far stars are away from us. So this methodology has now been given a name. Remember what we used to use by measuring angles? We used to call that the parallax angle of methodology. Well, they call this the method of spectroscopic parallax. So let me write that down. So instead of measuring angles, we basically measure color. So spectroscopic means that we measure the color of the stars in order to figure out their distance. It has nothing to do with measuring the angle, of course, but they just use this term to simulate that it's like measuring the angles for stars nearby using the parallax angle. So this is kind of an interesting concept. But again, this has really blown the doors off our understanding of stars. We now understand their sizes, we now understand their distances, we now understand that they go through a life cycle, and so this has really enabled us to understand stars a whole lot better. But it really opened for us the ability to figure out how far and how big things were. So once we're able to figure out the distance of stars that are far away from us using powerful telescopes, we then began to get a feel for how big our Milky Way galaxy was. And then slowly over time, we began to see those little fuzzy patches within what we thought was within our Milky Way galaxy. When we started looking at them, we had actually found a way to realize that those things are not inside our own galaxy, but they're actually beyond our own galaxy. And that those things are actually like our own Milky Way galaxy, but much farther away. So little island universes. So how did we figure out the distance to those, and how did we come out to realize that those are not just nebulas in our galaxy, but they're actually other galaxies beyond our own galaxy? So beginning to learn to appreciate how to find the distance to stars and then distance to objects, we then began to realize, wow, this universe is bigger and bigger and bigger than we ever thought it was going to be. So stay tuned if you're interested in this, and we'll show you some more clever techniques of how they figured out how big the entire universe was, one step at a time. Welcome to ilectureonline, and to give us a better understanding of how we can measure distances with the HR diagram, I wanted to come up with a little example here that hopefully will explain it. So let's say we have two stars, a sun-like star, or something like the sun, and a much brighter star, something that's 100 times brighter than the sun. Usually the L sub naught simply means the luminosity of the sun. So in comparison, this star would put out 100 times as much light as this star. If they were placed side by side, this one will look 100 times brighter than this one. All right, so what happens in real life? Well, let's say that we're looking at the two stars. Here's the sun-like star at some distance, and then there we have the very bright star, much brighter than the sun, but since it's so much farther away, let's say that it appears to look exactly the same brightness as the sun-like star. Now, before the HR diagram, and if the two stars were too far away so that the parallax angle could not be measured, so we really wouldn't know how far it was to the stars, you'd see two stars. One was a little bit, one was more like whitish in color, white blue in color. The other one would be yellow in color, but they would appear to be the same brightness, and you really had no idea to figure out which one was bigger, which one was smaller, which one was farther, which one was closer. You had really no idea. But now with the HR diagram, we're able to take a look at this star, look at its color, look at the wavelength of the light coming towards us, place it on the HR diagram, realizing that it's a B-class star, looks bluish white. We then come up here and then we realize, wow, it is 100 times as bright as a sun-like star. So now we realize we're looking at a star that's really bright, but it looks no brighter than the sun-like star. So therefore it must be farther away. How much farther away? Well, since the intensity of a star, which is analogous to the luminosity of a star, is proportional to 1 over the distance squared, we can then say that the distance to the brightest star is equal to the square root of the number how much brighter it is compared to the sun-like star, the square root of that times the distance to the sun-like star. So since this is 100 times brighter, it must therefore be the square root of 100 or 10 times as far away. That's what we mean by the intensity being proportional to 1 over the distance squared. So if we take the square root of that extra distance, that would then equate to, or if we take over, well, I'm not saying this right, let me show you what I mean. If we then rearrange these terms right here and we go distance squared is equal to 1 over the luminosity. So again, then if I take the square root, I can say that the distance is therefore equal to 1 over the square root of the luminosity. So that's why if I take the square root of the luminosity, I will get the distance or the extra distance. And so from that, I can then say I take the square root of the increase in luminosity. It's 100 times brighter. Take the square root of that, I get 10, so therefore it's 10 times as far away. Now that's how we use the HR diagram. There's only one problem. I still need to somehow establish the base distance for any star. For example, how far was the sun star? I now realize this is 10 times as far away, but how far is it to this star? In order to do that, we came up with a brightness scheme called magnitudes. We have what we call the apparent magnitude, we have the absolute magnitude, and once we understand that, and we throw that together with the understanding of how we measure the distance from one star to another relative to each other, you can then see how we use the HR diagram to actually figure the real distance to any star out there that we can measure its brightness thereof. So there you go. That's how we use the HR diagram to find the relative distance. In the next several videos, I'll talk about the magnitude scales, and then we'll put it all together, and then we'll be able to figure out the distance to any star based upon its color and its measured brightness. Welcome to Lecture Online, and in order to understand better how to use the HR diagram to measure distances to stars, we need to come up with a standardized method to establish the luminosity or the brightness of stars as it appears to us from our observations, and we need also a scale on how to determine the absolute brightness, how bright it actually is, irregardless of what it looks like to us. So in order to measure or in order to establish the actual brightness, you have to have some standard distance where you want to place the objects so you can see how bright they would appear if they were at that location. But first, before we get there, let's take a look at the scale that we use to actually measure the brightness of stars, because we need to start there at first. So in the old days, back in the days of the Greeks, they began to do that already. They began to classify stars by their brightness, and they came up with this brightness scale, where 1 meant the brightest stars in the sky and 6 meant the dimmest stars in the sky. And so they didn't have any fancy telescopes or good instruments to really measure the brightness. They just went by what they could see with the naked eye. And so they just kind of estimated based upon what it looked like. And so their scheme was that a star that had magnitude 1 brightness was twice as bright as a star that had magnitude 2. 2 was twice as bright as 3, 3 was twice as bright as 4, and so forth. It was basically a scale by 2, and that means that 1 was 4 times as bright as 3, 1 was 8 times as bright as a 4 star, 1 was 16 times as bright as a level 5 star, and 1 was 32 times as bright as a magnitude 6 star, for example. And so there's a few examples of how that worked. But with modern instruments and with telescopes, we began to realize that that scale really didn't work very well. And the estimations with the naked eye really didn't give us a good idea of how bright it was. So we came up with a new magnitude scale, and we called it the apparent magnitude scale. And we used a small letter m, I don't know where I have it here, right here, small letter m to indicate that's the apparent magnitude. So the scale worked the same way. Smaller numbers are brighter, bigger numbers are dimmer, but we realized we also needed negative numbers because some objects in the sky were actually brighter than a 1. They were brighter than a 0. So we kept on going. -1 is brighter than 0, -2 is brighter, -1, and so forth. So how did this scale work? Well, they had it in such a way that a difference of 5 magnitudes represented a difference of 100 times the brightness in the luminosity. For example, if one star has magnitude -2 and another star has magnitude +3, the difference between those two is a total of 5, right? 3 minus a -2 is 5. And so the ratio of the brightness of star 1 versus the brightness of star 2, that ratio, B1 divided by B2, is equal to 2.512 to the difference in the magnitudes. Now see, in that old scale they used just the number 2, but they realized they had to adjust it, so they adjusted it to 2.512 to the delta m. And so in our particular case, that would be equal to 2.512 to the 5th power, because that's the difference between 3 and -2, which is actually equal to 100, which meant that this star will be 100 times as bright as this star. As long as there's 5 magnitudes in between, one star is 100 times as bright as the other. For example, a magnitude 0 star is 100 times as bright as a magnitude 5 star. And a magnitude -4 is 100 times as bright as a +1, and so forth. So a delta of 5 magnitudes means 100 times brighter. Or the other way around, star B is 100 times dimmer than star A, for example, or star 2 is 100 times dimmer as star 1. What if the difference is not 5? Well, you can use your calculator. Let's say that we have a magnitude. Let's call this B3, and let's call this B4. So if star 3 has a magnitude +1, and star 4 has magnitude +4. And remember, these are apparent magnitudes. That's the way they appear to us from the Earth. That's not necessarily the way they actually are, but that's the way they appear to us. So you realize that since star 3 has a smaller magnitude than star 4, star 3 is brighter. The question is how much brighter? So the ratio, B3 divided by B4, is equal to 2.512 raised to the difference in the magnitudes. In this case, the difference between these two magnitudes is 4 minus 1, which is 3. So we have 2.512 to the 3rd power. Then, of course, you need your calculator. So 2.512 raised to the 3rd power is 15.9, or about 16. That means this star, star 3, is 16 times as bright as star 4. And that's how we use the magnitude scales. Now, for some comparisons. How bright is the sun? Well, the sun is, of course, really bright. It has a magnitude of -26.7. That's, of course, not the absolute brightness, the real brightness. It just appears that bright to us. Obviously, the brightest object in the sky. Second brightest is the full moon. At the full moon, it's -12.6. Third brightest object is Venus at a magnitude of -4.4. Fourth brightest object, well, there's a couple more planets that are also really bright. For example, Mars and Jupiter at their brightest are magnitude of about -2.5 or so. For Sirius, the brightest star in the sky is -1.4. Vega, one of the bright stars that you see primarily in the summer in the evening, has a magnitude of +0.03. They used to use Vega as the 0 reference mark, but with more accurate measurements, it turned out that it was actually slightly above 0, and so it's still the reference mark, but it's slightly above at 0.03. Betelgeuse in the constellation of Orion is 0.58. Regulus in the constellation of Leo is 1.35. Polaris, the North Star, magnitude +2.2. And the dimmest star that you can see with the naked eye is about a magnitude +6. If you go out in the desert or in the forest where there's no lights, no city lights or anything like that, You can see stars as dim as a +6, and then in the sky on a clear night, you can see about 3,000 stars. So about 3,000 stars on one side of the sky there have a magnitude of about +6, and of course if you go to the southern hemisphere, you'll see another about 3,000 stars with magnitude +6. So in total, you can see about 6,000 stars with the naked eye all around the sky. Pluto, very small, trans-Neptunian object, several billion miles away from here, has a magnitude of +15. The most powerful telescopes on the Earth tend to have a magnitude of +21, although now with special techniques they can go beyond that. The Hubble Space Telescope has a magnitude of +30, and they've actually gone a little bit beyond that as well to like about +31 point something. So you can realize you can see an enormous amount of detail with the Hubble Space Telescope because it can see objects so far away. But that gives you kind of a feel of how we use the magnitude scale. This is of course the apparent magnitude scale, and then on the next video we'll look at not the apparent but the absolute magnitude scale, and we'll compare the two, and then finally we'll notice and know how we use these scales and the techniques we've learned to find the distance to anything in the universe. So that's the key to understanding how we determine the distance to stars, galaxies, and anything else in the universe. And the second piece of the puzzle to understand magnitudes and brightness of stars is the term absolute magnitude. Now notice we use the capital letter M to indicate absolute magnitude, small m for apparent magnitude. So what's the difference? Well, here it says it all. Absolute magnitude is equal to the apparent magnitude if the star was at a distance of 10 parsecs, which is 32.6 light years. What does that mean? If you want to know what the absolute magnitude of a star is, you would take the star, whichever star it is, and place it at a distance of 10 parsecs away from the Earth, and then see what would the apparent brightness be of that star. That is then the absolute magnitude of a star. For example, our sun, because it's so close to us, has an apparent magnitude of -26.7. The absolute magnitude is 4.83. So that means if we took our sun, which is very close to us, and we then moved it 10 parsecs away, or 32.6 light years away, it would appear to us to have a magnitude of 4.83, which is pretty dim. Remember, +6 was the limit of our ability to see a star with the naked eye, so it would be a very, very, very dim star way out there, barely visible. Wow. So the sun isn't that particularly of a bright star. Most stars, however, are less bright than the sun, so they have absolute magnitudes of even greater numbers, +5, +6, +7, +8, +9. So you can see that the vast majority of the stars, if they were placed at a distance of 10 parsecs away, or 32.6 light years, would not be visible to us to the naked eye. That's why when we look out to the sky at night, we could only see about 3,000 stars. That's not because those 3,000 stars have a magnitude of less than 6. It's just that they're close enough to us so that we can see them, or they're so bright that even though they're so far away, we can still see them. So stars like the sun can only be seen to maybe a distance of maybe 11, 12 or so parsecs away, and at that point you probably wouldn't be able to see them anymore. Now, to give also another picture, another view of this, let's say that we have a relatively bright star in the sky. Now, we don't know, of course, that it's bright because it's a really big star, or it's bright because it's close. Now, obviously, from this picture, you can see that it's closer to us than 10 parsecs. Now, what would happen if we take that star and we move it farther away? Well, the apparent brightness would, of course, diminish. Whatever the apparent brightness is by the time we reach a distance of 10 parsecs, that then becomes the absolute brightness of that star. Let's say we look at another star, a really big star, but it's really far away. Now, of course, we wouldn't know that it's far away, but it would appear, it appears to us, and maybe I should draw a circle around that. See, this is the apparent brightness because it's so far away. Now, what would that star look like when we bring it to a distance of 10 parsecs? Would it look like this? Oh no, of course not. It would look a whole lot brighter than that. By the time we bring it to a distance of 10 parsecs, it probably looks like this. It would look enormously bright. And so there are some stars that are like that. For example, notice the star Antares. Antares is quite far away. It's still a fairly bright star in the sky. It's the brightest star in the constellation Scorpio. But notice, if we were to take the star and we move it closer to us to a distance of 10 parsecs, it would have a magnitude of -5. It would look brighter than Venus in the sky. It would be absolutely enormous. And then as a final comparison, take a look at how bright a supernova is, a type 1a supernova. You may not know yet what a type 1a supernova is. It's actually a white dwarf that explodes, but we'll get into that in a later video. But notice the brightness of one of those explosions. When a star explodes in a supernova explosion, at that time, it has an absolute magnitude of -19. Now, of course, most supernova explosions, they're really far away. But imagine if one happened at a distance of 10 parsecs. If a supernova explosion were to happen at 32.6 light years, a distance where if our sun was there only would have a brightness of 4.83, barely visible, it would have a magnitude of -19. Remember, our sun has a magnitude of -26, so it would have a brightness between the full moon and the sun. Actually, if a supernova went off that close to the Earth, only 10 parsecs away, at night, you could probably read your newspaper from the light emanated from the supernova explosion. Just to get a feel of how bright a supernova explosion is, let's measure the difference in brightness or luminosity between the sun at 10 parsecs and a type 1a supernova. And let's also compare, for example, the brightness of the sun to the star Sirius. Sirius is a bright star, the brightest star in the sky that is in the constellation Canis Major. All right, let's first compare the sun to Sirius. So the sun and Sirius. And that's the beauty behind what we call the absolute magnitude, because then you can actually compare the actual brightness between two stars. Not the way they appear to us, but the way they actually are. So if the sun has a magnitude of plus 4.83 and Sirius has a magnitude of plus 1.47, let's call that the brightness of Sirius and the brightness of the sun. And now let's compare the two. So the brightness of Sirius divided by the brightness of the sun, so that would give us the ratio of their luminosities is equal to 2.512 raised to the difference in the magnitudes, which is 2.512 raised to the difference would be 4.83 minus 1.47, and so that would be equal to 2.512 raised to the, if you subtract that from that, you get 3.36. And let's find out how much brighter Sirius is compared to the sun. All right, so 2.512 raised to the 3.36 equals 22 times as bright. That's interesting. So it's equal to 22, which means Sirius puts out as much light as 22 suns. Or if you were to put the sun next to Sirius, and if you want to get the same amount of light from stars like the sun, you would need to place 22 stars like the sun next to Sirius to put out the same amount of light. Now let's compare a type 1a supernova. How much light does it put out? And that will be absolutely enormous. So the light or the brightness of a supernova, of course we're talking about a type 1a, divided by the brightness of the sun, is equal to 2.512, and then of course the difference would be 4.83 minus a minus 19. And so that of course would be 2.512 raised to the 23.83 power. That's going to be a really big number, 2.512 raised to the 23.83 power. Wow, I need a scientific notation for this one. It would be 3.4 billion, 3.4 billion. So when a supernova explosion occurs, a type 1a supernova explosion, it puts out as much light, as much energy as 3.4 billion suns. That's absolutely enormous. Now that's, again, the beauty of the absolute magnitude. It allows you to compare two stars to one another, two galaxies to one another. As long as you know the absolute magnitude, you can actually have a good feel of how bright one is compared to the other. And then in the next several videos, I will show you how to use the apparent magnitude and the absolute magnitude to actually determine the distance of stars using the HR diagram. Welcome to ilectureonline, and here we're going to see finally how to find the distance to a star using the HR diagram. This is what all that fuzz was about, so to speak, all the last several videos. So here's a good example for us. Let's say we have a star that has an apparent magnitude of +8 and an absolute magnitude of -2, how far is this star? And I need a question mark there. All right, well, first of all, how do we figure out the apparent magnitude? We take a telescope, we look at the star, we measure the brightness of that star. We have means to do that using a certain filtering system. We can actually find the color of the star and the brightness of the star using our telescopes. And so we come up with this measurement. So, all right, that's how bright the star appears to us. Now, the second part is we need to find the absolute brightness of the star. So how do we do that? That's why we need the HR diagram, because we look at the color of the star, we measure it very, very precisely. We come down to the HR diagram, we find the color of the star, we come up here until we reach the main sequence, then we come up to the left side and we read off on our scale what the absolute magnitude is. Simply by knowing the color and by knowing it's the main sequence star, we can find the absolute magnitude, and so now also the absolute magnitude is known. Now we have to figure out how far it is to the star. Remember what the absolute magnitude is. The absolute magnitude is the brightness it would appear to us if it was at a distance of 10 parsecs. So if we place a star right on the distance, 10 parsecs away from the Earth, it would appear to us as a -2 magnitude star. But instead of looking as a -2 magnitude star, it actually appears to us as a +8 magnitude star. So it's a lot dimmer than it would appear to us if it was a 10 parsecs away, which then means it must be much farther away. So therefore the star is actually way out here, so it looks like a very, very dim +8 magnitude star. Matter of fact, with the naked eye, you wouldn't even be able to see it. You would need a binocular or a small telescope or so to see the star. So how do you then calculate the distance? Well, if the star is farther away than 10 parsecs, you use this equation. If it's closer than 10 parsecs, you use this equation. But we already established it was farther away because the apparent magnitude is dimmer than the absolute magnitude, so we knew that it had to be farther away. So we're going to use this equation right here. And all we have to do is take the 10 parsecs and multiply it times the square root of the difference of the intensity between here and here. Wow, how do we do that? Well, first of all, we want to find the difference in the magnitudes. So the difference in the magnitudes, delta M, is equal to 8 minus a -2 is equal to a 10. So the difference in magnitudes between the absolute and the apparent is 10 magnitudes. So then you find the difference in intensity. The difference in intensity is equal to 2.512 raised to the difference in the magnitude. So in this case, it's 2.512 raised to the 10 power, which is equal to 10,000. Wow. How did I figure it out without a calculator? Well, it turns out that for every 5 magnitudes, it's a difference of 100. So for 5 magnitudes, it's 100. For 10 magnitudes, it's 100 times 100, so it would be 10,000. For 15 magnitudes, it would be 100 times 100 times 100, which would be 1,000,000. So that means that the star is 10,000 times brighter if it was here at 10 parsecs than when it is where it actually is at. And so we take that number, the difference in intensity, plug it into the radical here, so we have 10,000, which means this is equal to 10 parsecs times 100, because the square root of 10,000 is 100, which is 1,000 parsecs, which of course is 3,260 light years. So that means, with the use of the HR diagram to establish its absolute brightness, simply because we knew the color and we knew it was the main sequence star, so therefore the absolute magnitude was -2. And then by measuring the apparent magnitude, by just taking a telescope, looking at it, measuring its brightness, we from that can then determine the difference in the magnitudes. We can then figure out the difference in the intensities between what it would be if it was at 10 parsecs and what it appears to us where it actually is at. Then we take this equation, 10 parsecs times the square root of the difference in intensities, and we get the actual distance of where that star is at. Isn't that great? And it turns out, by the way, if the star happened to be closer, again, you measure the difference in magnitudes, then you measure the difference in intensities, and then you use this equation, you divide by the square root of the difference in intensities to get the distance, which then will be closer than 10 parsecs instead of farther away. But that's how we do that. That's how we determine the distance to stars using the HR diagram. Welcome to Lecture Online, and just to make sure we fully understand this, how to find the distance to stars using the HR diagram, let's word the question a little bit different and see if we can figure it out. So here we have a star that is known to have 10 times the luminosity of the sun. So in the HR diagram, it would appear a little bit higher on the main sequence, 10 times the luminosity of the sun being equal to 1. Its apparent magnitude is 6.2. How far is the star from us? So at first you go, wow, that's kind of different. How do I do that? And then you go back to the basic and saying, for me to determine the distance of stars, I need to know both the apparent magnitude and the absolute magnitude. Since I was given the apparent magnitude, I first have to find the absolute magnitude. So what is the absolute magnitude? Well, since it's compared to the magnitude of the sun, let's go ahead, and we know that the absolute magnitude of the sun is equal to 4.83. Of course, that's a plus 4.83, not a minus. We don't have that bright of a star that will live nearby. And then we realize that the change in the intensity is equal to 2.512 raised to the change in the magnitudes. All right, so we are given the change in intensity. We know that's a difference of 10, so we can say that 10 is equal to 2.512 raised to the difference in the magnitudes. And now if we take the log of both sides, we can say that the log of 10 is equal to the log of 2.512 raised to the delta m. And of course, we can then take the delta m and put it in front of the log, so we can say the log of 10 is equal to the delta m times the log of 2.512. And finally, the delta m, therefore, is equal to the log of 10 divided by the log of 2.512. Now we get a calculator out. Okay, so we have 10, take the log of that. Of course, that should be 1. It's 1 divided by 2.512. Take the log of that, and that would be 2.5. All right, so that means the difference in the magnitudes between the sun and that star, and that's the absolute magnitude, is 2.5. So actually, I probably want to write a big M because we're looking for the difference in the absolute magnitudes. So since the sun is 4.83 and this one is brighter, then the magnitude of the star in question will be equal to 4.83 minus the difference in magnitude, because it's a brighter star, it's going to be smaller, minus 2.5. And so that means that the absolute magnitude of the star is equal to this minus this, which would be 2.33. And of course, that still be a plus. So now we know the apparent magnitude and the absolute magnitude of the star. Now we're ready to find the distance. Because now what we can do is find the difference in the intensity between this and this. Now, let's make a picture of what's really going on here so we have a full understanding of how to solve that. So we're observing the star from the Earth. So here we are on the Earth, observing the star. Here's 10 parsecs. And at 10 parsecs, the star has the absolute magnitude as brightness. So that's where the apparent and the absolute would be the same. So if we place a star at 10 parsecs, it would appear to be a 2.33 magnitude star. So here we can say, here's the star. And at 10 parsecs, the magnitude is equal to a plus 2.33. Now, it appears to us, from wherever it is, to have a magnitude of 6.2, which is dimmer. That means it must be farther away. If it looks dimmer, it will be farther away. So the apparent magnitude is equal to a plus 6.2, farther away. Now the whole question is, how much farther than 10 parsecs? How far is it away? Well, the first thing we do is find the difference in intensity between the star's intensity if it's at 10 parsecs and the star's intensity when it's farther away. So there we go. The difference in the intensity is equal to 2.512 raised to the change in the magnitudes. And that would be 2.512 raised to the 6.2 minus 2.33. And so this is equal to 2.512 raised to, that would be 4.2, that would be 3.9, 3.87. All right. So again, we grab the calculator, 2.512 raised to the 3.87, and we get 35.3. So the difference in the intensity is 35.3 if the star was at 10 parsecs versus the star being there. So in other words, it's going to be 35.3 times dimmer where it actually is than what it would be if it was at a distance of 10 parsecs. Now the final stage, since it's farther away, we can then say that the distance is equal to 10 parsecs times the square root of the difference in the intensity. So this is equal to 10 parsecs times the square root of 35.3. So now we take the square root of that, which is 5.94. So this would be 10 parsecs times 5.94, which means that star is 59.4 parsecs away. And that's, again, a nice example of how we use the HR diagram to find the distance to stars. No matter how they give it to us, as long as we can figure out the apparent magnitude by measuring it and the absolute magnitude by finding the relationship between how bright it is versus another star, or how bright it is if we place it at a distance of 10 parsecs. And that's how we do that.